Thank you, everyone, for coming here. Thanks, Sue, for organizing this. I got here yesterday, flew all the way from San Francisco. So it's quite a long trip. I think the first thing that I realized is something that we all know as developers. The time zones are hard. So yeah, thanks for making it so early in the morning. My talk is about error handling. It's probably not the sexiest of topics, so but hope you'll enjoy it. It's something that I think is very important. We don't spend a lot of time thinking about when we're building apps, but I like to think about it because I use a lot of software that's really buggy. I'm sure you do too. Xcode, and I always think about how much better software could be if we sometimes we spend a little more time thinking about the little details. And I think error handling is one of those things. So we're going to look into how we do error handling traditionally, how we've always done it in Objective-C, and a few ways of doing it in Swift. This is just some ideas that I've gathered with the time. It's not this is how you should do it, but I'm hoping that you'll find it useful and you'll be able to apply some of this when you work in Swift. So we're going to look at in particular asynchronous code because it makes error handling harder. See some issues that some may not have realized or run into when writing that asynchronous code and doing error handling. A couple of ways of dealing with errors in Swift, especially with Swift 2. And I'm going to show a lot of code in the slides. Don't worry if you can't follow it all. I'm particularly interested in the ideas, not the implementation details. But we're going to implement this Future API, a very simple implementation of it that shows how we can do asynchronous computation, asynchronous code in a way that makes it easier to handle errors. All right. So let's talk about the problem first. I have some code here that hopefully will look familiar to you guys. This is the classic completion block within completion block style of writing asynchronous code in Objective-C. This is written in Swift, but it's essentially the same thing. We're using completion blocks. And when we're doing this, each of those completion blocks can carry either some value that it returns asynchronously or some error if it fails to retrieve it. And the problem with this that we see immediately is that every time we need to check, okay, am I on the success case or am I on the error case? And that's why we end up with all these if-lets or if-else nested checks all the time. And this grows to the right very quickly as soon as you start having to do more asynchronous things within asynchronous things. So it's very easy to end up here. And this is not PHP. Swift is not PHP, but I'm sure you've all seen code like this before. So we can avoid this using some other techniques, and I'd like to show some of that today. But let's look at a couple of specific problems with this sort of API. If we look at the type signature of the completion block, we'll see that it passes two values that are two optionals. There's, in this case, we're downloading some image, and the completion block gives you an optional of an image and an optional of an error. And this is how it's always been in Objective-C. The only difference is that we didn't have optionals, but the thing is that they were always there. Every pointer value in Objective-C is implicitly optional because it can always carry nil. And that tuple, those two optional values, can have four different combinations. There can be an image and no error, no image and an error. That makes sense. But then we have these two last cases that don't make any sense, but they're entirely possible. We can have an image and an error, which I guess is good because at least we have an image, right? But we can have no image and no error, in which case something failed and we have no way of knowing why. I always like to remind, to say how I think of computers as perfect machines that never make mistakes. Because bugs are just what happens when there is a difference between what we thought we told the computer to do and what we actually told the computer to do. But the computer always does exactly what we tell it to do. And the thing is that when we don't have a great way of expressing our intentions, of telling the computer what we want it to accomplish, bugs are more likely to appear. So there should be a better way to express this, right? A way that eliminates these two cases that we don't want to be possible. I'll go into how we can do that in Swift, but let's look at some more issues with this. Checking the error first in that completion block, while not entirely incorrect, definitely compiles. It's sort of an anti-pattern in Cocoa, at least when using synchronous APIs. And thanks to Swift 2 and the new try-catch mechanism, this is no longer a problem. But before that, in Objective-C and Swift 1, we still needed to be careful because Cocoa says that you should check the return value first before looking into the error. Because sometimes you will have an error being returned from this API in a success case. This is an example of that. Here, this would look different with the Swift 2 new API, but that is just syntactic sugar. I think they still have some of the same, that new try-catch syntax has some of the same issues. But what I wanted to draw your attention to in this slide is how we check how we try to find out what error happened. And the problem with NSError is that it gives us no information at compile time. When an API tells you this thing can fail and I may give you an NSError, there is no way to know which type of NSErrors, and in particular which error domains and error codes are possible. And you could say, oh, we can look at the documentation, right? That's what ideally would be documented. But if we look at this API, for example, from NSString, if you look at the documentation, it actually makes no reference to either the error domain or the error code. So you can try to call it with an invalid path or something like that, and you may get an idea of what sort of errors you may find. But because the contract is very loose, it's not possible to know exactly which all the errors that are possible. And this means that you're always going to have to do some sort of fallback mechanism, a catch-all for errors, because you don't know if you're handling all of them. But more importantly, the NSError API makes it possible to do incorrect error handling. The code in the slide is actually wrong, but it's very subtle. We're checking the error code first, and the error code is nothing but an integer. And what this means is that because we're not checking the error domain, the actual error that happened could be something else, could be something different than ns-file read no such file error, but it happens to have the same integer value. But because we didn't check the error domain first, we can assume that, incorrectly assume that that was the error, where in fact it was something else. And if in the colon, inside the code, inside the if, we do something like, I don't know, format the drive or something like that, we could do the wrong thing because we're making the wrong assumption. So this may not seem very important, but I really think that robust software must take really good care of errors. Because I think when we ignore them, it's kind of a recipe for disaster. And I think we in general don't spend as much time making our APIs easy to use outside of the happy path. Some of the buggiest code bases that I've seen share a common problem. They lacked error handling. I've debugged code where it was very clear that the application was in a very wrong state, but there was no code in the application that was aware of that. So you have to literally dig into the code in dozens of classes and debug many methods, because the code is not aware that something went wrong a long time ago. It didn't log it. It didn't assert it. So I think we need proper abstractions to allow us to easily handle errors without adding complexity to our code. Because we want to make our programs correct outside of the happy path, because errors are going to happen. We've all seen errors like these in applications that we use. And some of my biggest criticism of Swift's new error handling features from Swift 2 come from this new error type thing, and I'll talk about why. But I found this tweet funny. It's a little subtle, but this is just iTunes showing out a screen that says Apple Music error occurred, and there's an OK button, and this is really extremely bad user experience. And you can't really probably blame the developers of iTunes, because the tools they had to do error handling are so bad that it's just really hard to do anything intelligent with an error. You get an NSError, and what can you do? Just say, hey, an error occurred. Don't know how else to continue. And Justin here just made a snarky comment about error type. Error type in Swift doesn't let you know at compile time which sort of errors are going to be possible. And it makes things like this just very natural to happen. This error type protocol was introduced in Swift 2, but Reactive Cocoa, which is a framework that I really like, introduced it before Swift 2. And I was really happy when Apple added this to the standard library. I really like this pattern because it allows other things other than NSErrors to be errors. And here's an example. We can create an enum, our own enum. In this case, it's called user info error domain. So we're going to have some API that lets you query user information. And the types of errors that API is going to expose are going to be these. And we can define them very explicitly. User does not exist, user request failure, etc. And so when we create this API, we can say, instead of this API is going to give you NSErrors, we can say, hey, this API is going to give you errors of this type. So when you use it, it's a lot easier to check for the exact types of errors that you can run into. And there's also this really cool thing that you can do with error type. It's actually kind of funny. So if we create a no error enum and we declare as error type, we can use this in our APIs as well and say this API is going to return errors of type no error. And that sounds really weird, right? But here's what's interesting about that no error definition. It's an empty enum, which means that because it has no cases, you cannot create a value of that type. So now you're like, wow, that's very useless, right? Why would you have an enum if you can't create values from it? But that's exactly the point. We can prove at compile time that no values of that type can be created. And that allows us to say, if you have an API like Future we're going to create later, that allows you to specify which type of errors are going to come in that future. If we say, OK, this future is going to have errors of type no error, it allows us to know at compile time that that particular computation cannot fail. And we don't have to check for errors. And we don't need a unit test to prove that. We know that at compile time. So I think that's really cool. So how do we use this stuff? OK. For synchronous APIs, there's this result type that it is very easy to define. It's just defined as that. But it's in an open source implementation in GitHub in that URL. And I've used it in a few apps, and it works great. And this allows us to fix the exact problem that I was talking about earlier. Because this is an enum in Swift, we can know that a value of this type has to be either a success with a value of type t, or a failure with some error type value. And we know that it cannot possibly be neither or both, like we saw at the beginning with those two error case conditions that don't make sense. This is obviously not in the Swift standard library, but I really like it. And I like it better than throws, which was introduced in Swift 2. And I'm going to show why. I think throws, even though it introduces really nice syntax, that's really nice to use, it has some of the same problems that we had before in Objective-C when doing error handling. So let's look at an example API that uses throws. This syntax allows us to say this function can either return an NS data or throw an error. And that's great because it actually solves the problem of it not returning anything and no error or both. But this doesn't have any error information. It has the same problem as NSError-based APIs. We know that it throws errors, but we don't know which ones. This is functional equivalent to what I just showed with result, except like we saw, result is generic over the type of data and the type of error. But because throws doesn't let you specify that, it would be like having a result where all we know about the error type is that it's a error type. So it can be any error type. When Apple first released this, I was happy because even though it lacks error type information, it at least forced us to consider the error case. And this is something that so many of the Objective-C APIs made it easy for us to ignore. For example, the APIs where you have to pass an NSError pointer by reference, so often you just pass null, right? You say, I don't care about errors. And well, that sometimes it's okay. I think it's, as software grows, when something goes wrong, that's exactly what I was talking about at the beginning. It's easy to just forget about that error. And then when something goes wrong later on, it's really hard to track it down to the first point when something bad happened. So I think that we should never ignore errors because they're really helpful to find out exactly when something goes wrong and go there and fix it instead of spending hours debugging some code. So I thought that at least do, try, catch had that benefit. It forced us to catch errors. But then Apple went on and they added this try question mark syntax. And this may be useful in some cases, and I've used it myself. I'm not saying you should never do this. You should be ashamed of yourself if you use it. But I think it's a little dangerous because it encourages us to ignore errors. And it's concerning because having a tool that makes it so easy to use, it's less code than do, try, catch. But in most cases, you shouldn't be using it. In this example, for example, when we get this contents NS data variable, at least we're going to have to check for nil, but we can't know if it's nil why that is or what happened. The program will continue on running without knowing that maybe your disk is out of space or something like that. This is how we would use the same API, but instead of using throws, using result. And I'm not saying that result is better than throws. I think both have their pros and cons. This syntax is a little more verbose. I think that try catch. But in this example, result at least allows us to specify that this API gives you a foundation error, for example. So we can go and check which cases are possible in a foundation error and do something useful with that. So I think I'd like to at least draw your attention to this important limitation of the language feature. It's there with us, and we have to live with it at least until Apple changes it. But I think it's at least important to be aware of it. I'll show at the end how we can mix and match result and try, so that we can have the added benefits of result with the nicer syntax of try. So this is what I'm hoping for in a later version of Swift. If we could just say which type of error this function can throw, we get the nice syntax without the problems of not knowing what happened. Okay. Oh, this looks weird. Okay. So let's talk about asynchronous code, because this is where things get trickier. And it's important to know that the throws syntax doesn't really support asynchronous code. It's meant to be used with a function that either returns something or throws, but if it doesn't return something immediately and it has asynchronously, it has to asynchronously do something to retrieve that value, it doesn't really help there. So let's talk about how we could implement a future API. I think futures are a great abstraction to allow us to deal with asynchrony much more easily. There are many libraries that implement this. And you may already be familiar with the concept, so I apologize if you've already used some of this, but I wanted to talk about it a little bit. I'm going to implement something very basic, but I think by looking at the implementation, it can be a little easier to understand, that there is no magic in this. All right, so what are futures? This is kind of a technical definition that they encapsulate a deferred computation. This is just a fancy way of saying that they abstract the work required to retrieve a value, which incurs in some delay to be able to get it. For example, some network latency or something like that. And this allows us to simplify the way that we describe the operations that are required to get that value. And what that means is that it allows us to treat those values that are asynchronous as if that are going to take a little bit to get, as if they were the value, as if we already had them. So it kind of, we'll see when we actually see it in code, that it kind of eliminates the complexity of having to pass completion blocks all around, having to wait for that thing to be there, and then doing that over and over. We have many asynchronous things happening. But more importantly, I think for the topic of this talk, they allow us to treat errors as first-class citizens. Futures have, or at least the particular implementation that I'm going to show here, we can make them take care of errors in a nice way, such that they are never ignored, but we also don't have to check for them every time. And we'll see how later. So they're easily composable as well. If we have many asynchronous things happening, one after another, they'll let us express that really easily. Okay, so enough talking. How would we implement this? Don't worry if you can't follow every line of code, because it's a little information dense. I have it available in my GitHub. So let's just focus on the concepts. I have some type aliases here to simplify the type signatures. But basically what we have here is the result type is what value is going to come out of the future. So it's going to be a result because it can be either a value or it can fail. And it's going to be some error. The completion type is what we're going to pass to the future once we're ready to retrieve the value. And the async operation is the block that is going to run to start the work to retrieve the value. Okay, and so we're going to create a future with that async operation block. So the future is going to encapsulate that work, and it's going to know what to do to retrieve it. And the start function is what we're going to call, is going to be the public API that we're going to call to tell the future, okay, I'm ready go do the work, I want to get the value. And this is how we could implement it. We just call operation, and we call the completion block when we're done. This is a very simplistic implementation. It doesn't take into account things like threading. For example, as soon as we want to do something useful with this, I'm not recommending that you take this exact code and you put it in your app. I'm just looking at the concepts. Because if you needed this in your app, you would need something like the ability to tell the future which queue you want the work to run on and which queue you want the completion to run on and things like that. So yeah, this is very naive implementation. Okay, so far that's not very useful. It's kind of just a fancy way of wrapping a completion block, really. So far, yeah, not a huge benefit from just having completion blocks in functions, right? But where futures get really exciting is when we implement some functions on them that allow us to do things with those asynchronous values in a nicer way than nesting completion blocks. So map is going to be that first function. What would we use map for? Let's look at this example. Say we have a function that allows us to request the information of some user, giving the user ID. User is a struct that we're going to get. In this example, all the user has is the avatar URL, because that's all we're going to use for the example. But you could imagine it would have other fields like the name, the email address, or something like that. So given that request user info function that returns a future, because it needs to perform an equal request, for example, if we want to create another function that instead of the user gives us the avatar URL, we could compose that first function, and all we need to do is call map and extract the avatar URL. And that's very simple, right? But look at the request user avatar URL. What's great about that is that even though the first function can fail, right, it returns a future of user and error domain, whatever the error domain is. The second function is not checking for the error. And that doesn't mean that it's ignoring it. It means that the implementation of the map function already does that for it, which means that we have this centralized implementation of what to do in case of errors, and that doesn't add noise everywhere else in our code. So the map block is only going to run if we actually have a user. If we don't, it's not going to extract the avatar URL, and we get that for free. Okay, so this would be the type signature. We would pass a block that takes the value of type T. In our previous example, that would be user, and it returns some other thing of type U. And the return of this map function is another future that instead of keeping values of type U, now it holds a value of type U. It's a little complex, many types here. But if you've already used the map function in Swift, you'll find it very familiar. So I wanted to compare the types so that you see that this is the exact same content. This is just working kind of in an asynchronous way. But if you look at the map function in array, which is very useful, lets us take an array of strings, for example, and map it into an array of integers, where the integers are the length of the string. And it gives us this really neat syntax where we don't have to, iterate with a loop and have a temporary array that we append to, et cetera, et cetera. Optional is very similar. It just behaves slightly differently. It only maps if we have some, and it ignores, it does nothing if we have none. So that's essentially what Future does. It's the exact same concept. And if you look at the type signatures, they have this nice parallelism. All right. So how will we implement it? I'm going to go over this very quickly because the code is available online. And like I said, I want to focus on the concepts. So we could create a new future. And what it's going to do, the work that this feature is going to do is it's going to start the previous future whenever the value is asked for. And when we get the result, we have to check if it's a success or failure. So we switch on the result. If it's a success, then we call the completion block. But instead of passing value, we use the f function that we were giving in map to transform it. If there is a failure, we can't call f because we don't have a value. So we just pass the error through. And this is where the error handling is happening. It's happening inside of the implementation of the map function. And this is how it looks all together. OK, so map is already very useful. Whenever we have an asynchronous value, we can transform it with a function that does something with it. The second thing that is really useful is when giving a value that we retrieve asynchronously, we want to do something with that value that is also asynchronous. The example that I'm going to do here is, hey, OK, I'm retrieving the user information asynchronously. And when that's done and I have the URL, I'm going to do this other asynchronous thing, which is download the avatar, given that avatar URL, right? So we have an asynchronous thing that when it's done, it does another asynchronous thing. This is the completion block within completion block that we had at the beginning. So how would that work with futures? We would just call this and then function that I'm making here. I'm calling it and then because I think it reads nicely. It's clear what it's meant to be used for. Some of you may realize that this function is what's known as flat map in many other places. It's exactly the same thing, but flat map doesn't mean anything. I think English is not my first language, but I don't think flat map is like in everyone's dictionary. So I prefer something like and then. It's a little more descriptive. And this is the type signature. It's very similar to map. But the block that we're passing, instead of returning a value, it's returning a new future. And same as before, we can implement it by returning. I'm going to go through this fairly quickly. Returning a new future, starting the initial one. We check for success or failure. And in the success case, now we call the f function, but what that gives us is not a new value. Now it's a new future. So we have to start it again. And then when we're done, we call the completion block. But if we fail, this is the shortcut that we have to take. We don't have a value. We have to stop everything. We can't continue with the work. So in the user example, it would be, if we haven't been able to retrieve the user information, there's no way that we can download the avatar. So we just return the error and bail out. And this is the code in one slide. It's actually very similar to map, and it's I find writing this code kind of fun. So I encourage you to try to implement it in a playground. What's interesting about it is that we can actually implement map in terms of flat in terms of and then, and vice versa. We can implement one using the other. All right. So I've shown you future. Looks cool, I guess, but what does it really give us? Let's look at the example that we started with to see how I think it really simplifies that asynchronous code. This is what we had at the beginning, this mess of nested callbacks that, it turns into that image that I showed at the beginning as soon as you have 2 or 3 or 4. And here we're checking for errors every time. And if we have an error, we call the completion block with nil in the error. And we do that. You see that repeated code twice here. It would turn into this. We would compose the functions that download user information and download avatars just by using map and then. And it's almost as if this code has no error handling, because the error handling is happening inside the implementation. So even though it makes it easier, it kind of goes against what I said at the beginning. Please do error handling. And here we're not doing any error handling. But the great thing is that because it's happening under the hood, we cannot forget to do it. The load avatar function is going to carry through any errors that happen in any of the other functions that it's using to implement itself. And it also gives us the compile time guarantee that we know that we're handling either the success case or the error case correctly. Well, I'll take questions in a second. I'm almost done. Oh, I thought you were going to ask a question. Okay. Yeah, we're almost done. And it's not possible to run into the case that we saw at the beginning where we have a success and an error case or none, thanks to result. Okay. So I think Future is a really nice way to do error handling in Swift. Throws from Swift 2 doesn't help here. But we're going to see how, if you really like the throws and try syntax, how we could use it with result. And this is implemented in the result implementation that I linked to in the previous slide. But the code is actually really simple. If we want to create a result from a function that throws, we could implement a constructor for a result like this. And if we want to go the other way, I think this one's the most interesting probably. If we have a result that some function returns, we can implement a dematerialized function, or probably with a better name, that throws or returns a value of type t. So now with a result, we can use the try-catch function as well. And this allows us to go from the result world to the Swift2 function, the throws world, and vice versa. This is an example of that. Using the feature that we just showed, because it gives us a result, we can do the do catch syntax here. Okay, so now that I've shown features, I want to mention a couple of things that I've run into, that I've learned in the past year. I've seen many Swift feature implementations in GitHub, and while they're great, I think when you're building an application, you run into so many use cases that you quickly run into limitations of them. I think they're a very useful abstraction, but we can, and it can help you improve your asynchronous code, but they don't work everywhere. More importantly, they only represent computation to retrieve one value. So it also represents something like a continuous stream of values. And an example of this would be a gesture recognizer. A gesture recognizer is something that gives you values, like the position in the screen of the finger, asynchronously, because you don't know when the user is going to touch the screen. But it's not just one value, like this feature would give you. It's many values, as many as positions on the screen the gesture gives you. So features are not going to work there. Can encapsulate streams of values. And another subtle difference is this difference between consumer-driven and producer-driven. The one that we just did, it was all consumer-driven. We had a feature, and then we asked the feature, OK, now give me the value. That's pull-driven. But sometimes, like going back to the gesture recognizer example, we don't ask the gesture recognizer, OK, now give me a value. It's the gesture recognizer that will give you values when it's ready, when it has something to give you. So that would be producer or push-driven. And features are not really meant for that. So if features don't work for that, what can we do? Well, this slide is also wrong on this resolution. Reactive Cocoa, not reactive Cocoa A. I really like Reactive Cocoa. I'm not trying to sell it here. But Reactive Cocoa gives you this tool called Signals, and they're a superset of features, and they're really useful. They cover all these use cases that I just talked about, and that makes Reactive Cocoa a really powerful tool for asynchronous programming. So I just encourage you to go check it out. It has a learning curve, but hopefully the things that I've mentioned today will be useful when trying to become familiar with it and understand it. So that's the URL for Reactive Cocoa. And I really like this blog post. It goes over this, the concept, it calls this concept railway-oriented programming. It's another way of thinking about what I talked about with values and errors. And it uses this really interesting metaphor with railways. I'll share the slides. I'll tweet about them, and they'll be on GitHub if you want to, copy the link. And that's it. Thank you very much for listening. I'll be happy to take questions. I don't know how long we have.
We have about maybe 2 questions.
Okay.
So we don't have a roaming mic, so just yell out your question.
Yeah, I'll repeat it so that it's on the audio.
Any questions? Okay, if not, then thank you very much.
Right.
One question.
Yeah.
If you during one of those steps have to add extra errors, how would you handle that?
Sorry, can you say that again?
You have to distinguish and then continue. So if during the first step there are certain errors that occur, but then the next step other errors can occur, how do you combine those two?
Yeah, that's a great question. So the question is, if you have a function that returns a future with that has specific type of errors, and we want to use and then to concatenate another asynchronous function that gives different types of errors, how does that work? And yeah, and then it's not going to work. It'll fail to compile, in fact. But we could implement a different operator that lets you transform the error so that those functions become compatible. And even though this is cumbersome, I can answer the question more verbose on Twitter. But it's actually useful because it forces you to think about the error domains and which type of errors make sense in each layer of your application. So it'll be hard for you to have errors that are of type, something that is very low level, some like kernel level errors, and have them surface all the way to the UI without having to wrap them and put them inside something that makes more sense in the UI layer, like IO error, something more generic that's easier to parse. So when you have lots of layers, it'll force you to have error domains that are more specific to each of those layers. It takes a little more work and more code, but I think it's actually a nice thing. Any more questions? Yeah, one quick question.
In Objective-C, reactive Cocoa was really heavily based on KVO, right?
Mm-hmm.
I'm just wondering what's the performance like?
Of the performance of reactive
Cocoa in general in your app? iOS.
If you're using KVO a lot, or maybe in Swift.
Well, I mean, you're not using it, but it's part of reactive Cocoa, so I'm just wondering what the overhead is like, because I know it's KVO in general.
Okay, so the question is about the performance of using reactive Cocoa in your application. And it was making a point that in Objective-C it relied heavily on KVO. It doesn't anymore in Swift, even though you can use it. It depends on what you're doing. It definitely adds a layer to your application, so there's a little bit of overhead. What I found is that reactive Cocoa itself is really going to become the bottleneck. The bottleneck is usually the actual work that your application is doing. If you're doing blurring of images or downscaling huge images or something like that, that's going to be orders of magnitude slower than the added overhead of reactive Cocoa. Yeah, does that answer your question? Yeah.
I'm sorry, maybe you could pass during the break. Thank you.
Yeah, feel free to come to me and ask any questions afterwards. Yeah, thank you so much.